All right, so in this video, we're going to talk about inverse functions. And as I go through this, you'll notice quickly a lot of it is review from what you would have seen in college algebra. But even before we get to inverse functions, it's probably necessary to take a step back and review what a one-to-one function is. And so function f we say is one-to-one if f of x sub 1 does not equal f of x sub 2 when x1 is not equal to x2 in their allowable domains. So these are y coordinates, right? These are x's. If you take the x's and plug them into the function, they spit out y's. So f of x1, f of x2, these are y's. So if the y coordinates are different when the x coordinates are different. And so in words, that's a little bit hard to I guess, get a good idea what's happening. And so if you remember back from college algebra, even if we had the graph of something, let's say that we had a parabola here, and we can determine very quickly if this is one-to-one by running a horizontal line through it. If a horizontal line intersects the curve in more than one spot, you can see that it would not be one-to-one. And that's the case where the y coordinates would not would be equal in this case. So since the y coordinates are equal, we know that this function is not one-to-one. Okay? Now, if f is one-to-one, then the function is invertible. And that's really important to understand. We don't really discuss inverse functions unless the original is one-to-one. And so an inverse function, denoted by this f with the upper -1, that is going to be defined as the inverse at x equals y if and only if the function at y equals x. And so that's just your basic general notation for an inverse function. We'll see this again here in the next couple of videos when we talk specifically about logs and exponentials. The other thing worth mentioning is because of how the inverse function is defined by interchanging these x's and y's, the domains and ranges will also be interchanged. And so that's something to take into consideration. So there's just a real brief rundown on inverse functions and then, of course, one-to-one. I'm going to go ahead and clear the screen and we'll take a look at an example. Okay, so we've got our function here, 8x minus 3. We're told to find the inverse and to check it. So we'll start by finding the inverse. And so to find an inverse, you want to interchange the coordinates. So the y becomes the x and the x becomes the y. And then we would just take this now and solve it for y. So if I add 3 to both sides and I divide by 8, there sits the inverse function. So we've got our inverse function. Now we want to check it. And so remember, there's two things in order to confirm this is the inverse. There's two things that we have to show. The first one is that when we evaluate or we plug in our original function to our inverse, we need to make sure that this gives us x. And we also need to make sure that if we evaluate the other way, it gives us x as well. So those are the two things that we would need to show in order to check. And so I'll start with this first one here. This is where I'm going to take the original function. This is the original function right here. And I'm going to plug that into the inverse. So when I take that and I plug that into the inverse, I'm going to get a 1/8 times 8x minus 3 and then plus a 3/8. Well, when I distribute now, that's going to give me an x minus 3/8 plus 3/8, which when these are added, they zero out, leaving us with just our x. So far, so good. We're halfway there. For this next one now, I'm going to take the inverse, which is this, and I'm going to plug it into the function up here. So that one's going to look like 8 times 1/8 x plus 3/8 and then minus 3. When I distribute that 8, I'm going to get an x plus 3 minus 3. Those zero out, leaving us with our x again. So having now not only found the inverse but checked it, now we know that we've done this correctly and we're ready now to move on to the next thought behind what an inverse can do for us. Okay, so what I have up on the screen now is just a graph of the two functions that we were working with. I've labeled them. This is your original f of x, and this would be the inverse that we found. And if you remember what the graphs are supposed to do, they do that in fact. They're supposed to be symmetric about the line y equals x. So this is our line y equals x, and you can see that if I take, let's say, both of these and I fold it across that line, they should lay perfectly on top of the other ones. And so this again is very, very important to understand because it's going to happen every single time that way. We find an inverse by interchanging the coordinates and then solving, in this case, given an equation. But if you interchange the coordinates, the symmetry across the line y equals x should always be there. The other thing worth noting that we're actually going to generalize here in a little bit is the fact that the slope of this line is 8 and the slope of this line is 1/8. The fact that they're reciprocals, given they're not vertical or not horizontal lines, is significant. That's going to be the case every single time. And so when it comes to these types of functions, there's always these little relationships that are interesting to discuss, and that being one of them. Now I'm going to go ahead and clear the screen, and we'll generalize that idea a little bit more in a more mathematical way. Okay, so to generalize us finding the derivative of an inverse, we're going to essentially have a formula that we come up with here in just a few minutes. Now, I don't push this formula very hard because if you really want to figure out the derivative of an inverse, many times it's easier to just find the inverse and find its derivative. So just keep that in mind as we go through this. Now, to find the derivative of an inverse, I'm going to start with one of the forms we used a moment ago to check, where I'm going to have now my function evaluated at the inverse. We know that this has got to equal x. Okay, if the function and its inverse is truly what they are, then we know this result has to be x. So then I'm going to take this whole thing and I'm going to ddx it. On the left-hand side, we have a chain rule. Okay, remember compositions are always chain rules. And so we've got the derivative of the outside, which would be f prime, keep the inside the same, and then back times the derivative of the inside. So a ddx f with that upper minus 1, remember that upper minus 1 is going to be the inverse, and then equal to 1. Derivative of x with respect to x is 1. So again, this was a chain rule. Derivative of the outside would be that f prime right there. Keep the inside the same, then back times the derivative of the inside. The derivative of the inside would be this right here. Okay? So now, if I want the derivative of the inverse, then all I need to do is solve for the derivative of the inverse. So I'm going to divide off the f prime of the inverse of x. And so this is a formula now that you can use as you see fit in order to figure out what the derivative of the inverse is. You can simply do 1 over the derivative of f evaluated at the inverse. So again, it's interesting to see, but it's one of those things that I don't personally use all that often. Many times, again, it's easiest just to find the inverse and then find its own derivative from there.